Now, good morning to learners, and welcome to my lesson 5, where I'll be taking you through the electrolysis of aqueous solutions. So far, I just did mention about the lesson 1. I did mention about the binary electrolytes. I did mention about the binary electrolyte. I don't want to get back to this, but I just say that here binary electrolytes. These are electrolytes here containing one type of anion and one type of cation. That would mean, obviously, that our anion would, that anion, for example, if I talk about something like lead-2 iodide, lead-2 iodide here in molten state, this one here in molten state here, will have the lead ions as the only positive ion. At the same time, I would have the iodide ions as the only negative ions. Of course, this would go to the cathode. This would go to the cathode, while this one would go to the anode. And I think I did mention that. Now, this one here, this is what we call a binary electrolyte here. A binary electrolyte here contains one type of cation and one type of anion. Now, there is the difference that comes in whenever we are discussing about the aqueous solutions. Whenever we're discussing about the aqueous solutions. Now, where does the difference comes? Where does the difference comes? Now, we need to understand here that because when I talk about the aqueous solutions, of course, I'm talking about the solutions formed when I dissolve ionic compounds. Now, why does the difference comes? It's important to know that water is a weak electrolyte. It is a weak electrolyte that partially dissociate in water. That partially dissociate, forming hydrogen ions and hydroxide ions. This is what we're talking about here. Now, and an equation to that effect maybe can be like this one here. Water may be dissociating. Let me use potassium. Just use two arrows there, and I form hydroxide ions and hydrogen ions. Now, this is what I'm talking about here. Now, this is actually the major reason why maybe we expect some differences as far as the aqueous solutions are concerned. Now, when these ions are introduced, in my electrolyte, then we may expect some changes, especially when, for example, hydroxide ions may lose electrons better than the other anion. Of course, the difference comes in. If hydrogen ions, of course, gets into the solution and it can gain electrons more readily than the other, automatically it will be discharged. That's what I'm talking about. Now, that means here, for example, if I would be talking about something like sodium chloride, think about sodium chloride here. Now, this sodium chloride here, in molten state, of course, the liquid state here, it will have the sodium ion and will have the chloride ions. Of course, in the liquid states. But if I have sodium chloride in aqueous state, in other words, sodium chloride solution, I'm going to have the sodium ions, I'm going to have chloride ions, I'm also going to have the hydrogen ions, and I'm going to have the hydroxide ions too. So I'm going to have sodium ions, chloride ions, hydrogen ions, and hydroxide ions. That's basically what I'm talking about. Now, so in this particular lesson here, I will be discussing the factors affecting the discharge of ions at the electrodes. I'll be discharging the factors affecting discharge of ions at the electrodes, that is as far as the electrolysis of aqueous solutions are concerned, as far as the electrolysis of aqueous solutions are concerned. And maybe later on here, if time allows, I'm going to discuss how do we determine the quantity of substances formed at the cathode and at the anode. Therefore, welcome to my discussion on factors affecting the discharge of ions and the electrons. Now, the first factor that you're going to look at as far as the factors affecting discharge of ions and electrons is concerned is the position in the electrochemical series. I did mention here that if you're going to arrange these ions in order of their standard electrode potentials, you actually get what we call an electrochemical series. Now, it's also maybe important to mention here that there is quite a good relationship between electrochemical series and reactivity series. In one way, they're almost similar. They're almost similar, but we may have maybe some slight difference here, because I think if we refer to the electrochemical series in my previous lessons, you could have realized that, for example, lithium could be somewhere above here, above potassium, and actually we know that in the reactive series, potassium is more reactive than lithium. So there is a slight difference, but basically this is what we're talking about. Now, so if I take you back to the standard electrode potentials, in this order here, potassium actually has the most negative standard electrode potential, and you go that way, for example, you go that way there, hydrogen has a 0, then copper ions, these ones here will have positive values. Between copper, there's copper below hydrogen, because hydrogen is a 0. All these above hydrogen have negative standard electrode potentials, but the same that are below hydrogen, that is copper, we have mercury, we have silver, they have positive reduction potentials. They have positive reduction potentials. Now, and we actually said here that the negative, when we talk about the negative here, a negative standard electrode potential means that these substances here can lose electrons more readily than hydrogen. It also means that hydrogen ions can gain electrons. Hydrogen ions can gain electrons more readily. Hydrogen ions can gain electrons more readily than them. And then them that have positive values here means that they can actually gain electrons more readily than hydrogen. Get note of that. Very important. Now, when I talk about maybe the radicals or maybe the negatively charged ions, maybe this one we're not able to look at it, but basically this is how it goes. Now we have sulfate here, has the most positive reduction potential. Most positive reduction potential is the most positive, followed by nitrate, chloride, bromide, iodide, and we have hydroxide ions. Now hydroxide ions are the most negative. I mean, and again, of course, here, when you talk about the most negative here, it means that hydroxide ions can or have the highest tendency to lose electrons, to lose electrons. And of course, when it comes to the sulfate here, which is most positive, this one can easily gain electron compared to the others, but it is difficult for it to lose electrons here relative to hydroxide ions. Now, let us put this factor in place and we see what we're talking about. Now, let's, for example, think about electrolysis of magnesium sulfate. Electrolysis of magnesium sulfate. This one is an example here. Now, let's start by maybe thinking here, or maybe trying to argue out what are some of the ions in the magnesium sulfate solution. What are some of the ions in magnesium sulfate solution? Now, definitely here, because we have from magnesium sulfate here, we have the magnesium ions. We're going to have magnesium ions. We are obviously going to have the sulfate ions. And this one being an aqueous solution, This one is an aqueous solution, of course. Every time you hear of aqueous solution, we have hydrogen ions and we have hydroxide ions. This one, of course, comes from water. This one comes from water. Don't forget, I just mentioned here that water is a weak electrolyte and can actually be able to dissociate partially into hydrogen ions and hydroxide ions. Now, let's think here. Which of these ions will be attracted to the cathode? Now, I say that cathode here is connected actually to the negative supply of the battery, and therefore it is going to attract the positive ions. That means my positive ions here, magnesium ions, and we have hydrogen ions will be attracted to the cathode. Now, as they get to the cathode here, it is important to mention here that only the ions with the highest tendency to gain electrons, only those ions, that ion with a high tendency to gain electrons will be discharged. This is what will actually happen. Now, let's go back to our electrochemical series here. Now, remember the cathode here, we have the gain of electrons. I think it's important to note that because, and remember here we said that when we talk about positively charged ions here, they have a deficiency of electrons. For example, when I talk about magnesium ions, I mean that this one here, this magnesium atom, has already lost 2 electrons. Hydrogen here has already lost an electron. And basically what will happen here, the cathode here, they are going to regain the lost electrons, to form metal atoms. Now, so when it comes to the gaining of electrons, maybe we can argue out here between magnesium ions and hydrogen ions. Which of these actually will gain electrons more readily than the other? Now, here, of course, you look for the one with a higher positive standard electron potential, and of course, this one is hydrogen. Remember, this one has 0. If you go back to magnesium here, maybe you can refer, but of course it is minus 2 point something like that. Now, so of course we'll go for hydrogen ions, and maybe you can at this point maybe I can mention here that in aqueous solutions, when it comes to this factor, maybe eliminating other factors, you realize that hydrogen ions will always be discharged, not unless we have copper ions, which are more positive than hydrogen. Then we have mercury ions or silver ions. So in most of the cases, it's important to understand, or maybe to at the back of the mind here, we should register this, that in normal circumstances, hydrogen ions will be discharged because, with an exception of maybe something copper ions and maybe mercury and maybe silver ions. That's what we're talking about. Therefore, here, what will happen here is that the hydrogen ions with higher tendency to gain electrons will gain electrons and will form hydrogen atoms. Of course, here what's need to be done here is that we can talk about 2 of these hydrogen ions gaining 2 electrons and forming a molecule of hydrogen. Now, let me mention about the anode. Now, anode, of course, here this is a electrode connected to the positive terminal of the battery. Now, being connected to the positive terminal of the battery here, it will actually attract the negative ions. That means it will be attracting the anions. I'm going to have the sulfate ions, and I'm going to have as well hydroxide ions. Now, again, our argument here is, now, it's important to note that the sulfate ions, when you talk about negatively charged ions like this here, that means that they have an excess of electrons. When you talk about sulfate, it has an excess of 2 electrons. Hydroxide ions, it has an excess of 1 electron. And basically what they do here at the anode, as they get to the anode here, they are going to lose the electrons that were earlier gained, and of course they're going to form atoms. Now, therefore, here we are talking about the gaining of electrons. At the cathode we have at the anode here we are talking about losing of the electrons that were earlier gained. Therefore, we are asking ourselves, between sulfate and hydroxide ions here, which of these will lose electrons more readily? Now, the one that loses electrons moderately here is the most negative. The most negative. And of course, as far as these anions are concerned, hydroxide ions is the most negative. Hydroxide ions are the most negative. In other words, hydroxide ions rarely lose electrons compared to these other anions. And therefore, automatically here, hydroxide ions here will lose electrons here. And once it loses electron, of course, it is going to release, or it's going to form an oxygen atom and a hydrogen atom. Now, these two here can recombine. And when they recombine, we are going to have the compounds of hydrogen and oxygen. For example, water. We are going to have water here, and we may have, or we're also going to have oxygen gas. We're going to have oxygen gas. Now, if you try to think of this here, trying to balance this here, you've got to realize here that we're going to multiply by 2 here, so that we have 4 oxygens. I have 4 oxygen and I have 4 hydrogen. Now, when it comes to this level here, if I'm talking of hydroxide, each of this hydroxide here is actually losing 1 electron. When there are 4 of them, they're going to lose a total of 4 electrons. They're going to lose a total of 4 electrons. That's what I'm talking about. Now, therefore, what we're trying to say here is that both at the cathode and anode here, we are going actually to see a production of gases. We are going to produce, or we are going to see production of gases. Now, maybe for the sake of just balancing the electrons here, we can try and make, because what happens here is that the electrons that are lost at the anode are the very same electrons that will be gained at the cathode. Therefore, the most accurate equation to write here is multiply by 2 the whole of this equation here, so that here 2 times 2 here, obviously I get a 4. Here I'm going to multiply by 2 here again. So I'm going to have 4 electrons. I'm going to have 2 molecules of hydrogen gas. One of the things that you need to understand here, when it comes to the discharging of hydroxide ions and hydrogen ions, what you realize here is that the volume, look at that, the volume of hydrogen gas produced here is double that of oxygen gas. Very important. The volumes of hydrogen gas are the volumes or the number of moles. Remember, when it comes to the gases, we know from Avogadro's or even Gay-Lussac's theories, we know that equal volumes of gases contain equal number of particles. And therefore, when we talk about the moles in gases and their volumes, they are proportional. That means that even producing 10 cubic centimeters of oxygen here during this electrolysis, I'll be able to produce 20 cubic centimeters of hydrogen in the very same electrolysis. That's what we are actually talking about. In this particular case here, the solution here, the pH of the solution will not be affected. It's important to mention here that as far as these ionic compounds are concerned, you realize that most of them will be neutral, because when this water is dissociating, or when it is ionizing partially here, it is going to release the same number of hydrogen ions and hydroxide ions. That means here, if we are still discharging, hydrogen ions at the cathode, and we're also discharging we are also discharging the anode. And you can see that there's a hydrogen ions being discharged, 4 hydroxide ions being discharged. That means here that actually the neutrality will be maintained. The neutrality will be maintained. In a scenario where maybe hydrogen ions will be discharged while hydroxide ions remains, the solution becomes basic. In a scenario where hydroxide ions are being discharged while hydrogen ions remains, the solution becomes acidic. That is what we are talking about. Maybe at this juncture here, maybe it's also maybe to mention here that the electrolyte, the magnesium sulfate, its concentration will actually increase. Why is the concentration increasing? Now, the concentration is increasing because water is being removed. Water is being removed by discharging hydrogen ions and hydroxide ions. So by so doing, every time you remove water from a solution, concentration increases. That is what we are talking about. Let me get to the second factor. Now, our second factor here is concentration of electrolyte. Now, this one here will only affect, for example, when I talk about the anode, and of course the anode, of course, will be able to attract the anions, or the negatively charged ions. Now, if these ions happens to have close standard electrode potentials, in other words, for example, the anode maybe they have almost, or their ability to lose electrons is more or less, there's not much difference in terms of age. Then what happens here, the concentration factor will come in. Now, let me try and explain here through, for example, the electrolysis of brine or concentrated sodium chloride. Now, if this one here is my brine, which is concentrated sodium chloride here, which is actually concentrated, and then I'm going to have, of course, my inert electrodes. I'm going to have my inert electrodes. This is now. Let's look at this here. This is my positive terminal, of course, and this is the negative terminal, and this is brine here. Now, if you're going to switch on our switch, if you're going to close our switch, now this one's, let me put that here. These are graphite electrodes. We have them there. Now let's see exactly what happens at the anode. Let's start with the anode here. Now, as we have just seen here, concentrated sodium chloride here we'll have sodium ions. Of course, we're going to have chloride ions. We are going to have hydrogen ions, and we're going to have hydroxide ions from the water. We're going to have hydroxide ions from water. Now, so at the anode here, we are going to have, let me put this one here, this is electrolytes, or concentrated sodium chloride. So at the anode here, we are going to have the hydroxide ions, and we have the chloride ions being attracted here because they are negatively charged. Now, if you go back maybe to what I've just mentioned here, the hydroxide ions and the chloride ions, their standard electrode potential, their difference in the standard electrode potentials is not much. Actually, it is less than 1 volt. It is less than 1 volt. Less than 1 volt, actually. So basically, what will happen to this? What will happen to these two here? Much as the hydroxide ions have a higher tendency to lose electrons, because of the high concentration of chloride ions, the chloride ions will be discharged in preference. So basically, the equation will be, we are going to have chloride ions losing electrons and forming a chlorine atom plus an electron. Now, two of these chloride ions will obviously form 2 chlorine atoms, and then the 2 chlorine atoms here, for the sake of stability, they will form a chlorine molecule here, and of course 2 electrons will be released. 2 electrons will be released. That's what we are actually talking about. Now, so kindly just note here that this one is just happening because the 2 here, their tendency to lose electrons, the difference is not much. It is actually not much. I've just mentioned here that their standard electrode potential here is less, the difference is less than 1, and therefore this one can happen. Now, it's important maybe to note that as this electrolysis progresses, when the concentration of chloride ions reduces, when the concentration of these chloride ions reduces, automatically the hydroxide ions will start to be discharged. Hydroxide ions will start to be discharged. That's what we actually are talking about. Now, let's also think about the cathode. Now, at the cathode here, of course, the positive ions will be attracted here. I'm going to have sodium ions, and I'm also going to have the hydrogen ions. Now, if again you go back to the standard electrode potentials of this one here, sodium and hydrogen here, you realize that the difference between sodium ions and hydrogen ions is very big. Actually, if maybe you can go back, I think sodium was about negative 2.71, while hydrogen, of course, is a zero. Therefore, we are talking about a difference of 2 volts plus. Now, this is very high. This is very high, and therefore, in this particular case here, even though the concentration of sodium ions is quite high, the hydrogen ions will still be discharged. In other words, what you're going to have here, you're going to have hydrogen ions gaining electrons here and forming a hydrogen atom. Now, 2 of the hydrogen ions will gain 2 electrons and form a hydrogen molecule. Of course, it will be formed when the 2 atoms of hydrogen are combined together and form the hydrogen gas. That's what we are actually talking about. Now, that means here that with the observation here, what are you going to observe here? At the anode, you're going to observe a green yellow gas being produced. Because chlorine is actually green yellow. And of course, at the cathode here, you're going to have colorless gas. Not colorless gas, actually, colorless bubbles. You're going to see colorless bubbles being formed here. Colorless bubbles being formed at the cathode because of the production or the discharging of hydrogen ions to produce hydrogen gas. That's very important there. Now, maybe I can also mention something about the pH. You realize in this particular case here, remember pH has something to do with the hydrogen ions and hydroxide ions. Now, in this particular case here, the hydrogen ions are being discharged, while the hydroxide ions are not discharged. That means when you continue to discharge hydrogen ions, the hydroxide ions will be more. The hydroxide ions here increases here relative to hydrogen. And therefore, maybe if you talk about the pH, here, the pH of electrolyte increases. Talking about the neutrality, if the pH was 7, of course, the neutral here, a neutral solution has a pH of 7, we would expect the pH to increase to an 8, 9, and so on and so forth. That means that testing here with maybe the litmus papers and all this, you realize that maybe the solution becomes basic. That's what we are simply talking about. Of course, you don't expect maybe the concentration of the electrolyte to the concentration of the electrolyte, of course, to reduce because we are discharging the chloride ions, and we are also removing water by discharging of hydrogen ions. So basically, that is what we are talking about as far as now. Maybe just for comparison purposes, so that maybe we understand what we're talking about. If I was dealing with dilute sodium chloride, the hydroxide ions and the chloride ions here, hydroxide ions, of course, with higher tendency to lose electrons here, would actually lose electrons, and as we mentioned here, it will form water plus oxygen gas. I've just talked about balancing here. We're going to release 4 electrons. I don't have to dwell much on that. Actually, this is what I'm talking about. There's a big difference when you talk about the concentration. Concentration can actually affect the whole thing. However, at the cathode, nothing is affected. Because there's hydrogen ions, and we have sodium ions. Hydrogen ions with the highest tendency to to gain electrons will be discharged, so that we're going to have hydrogen gas. Maybe you can refer to the other equation, the other equation that we wrote here. 4 hydrogen ions in order to balance the electrons here. 4 electrons, so we're going to have 4 hydrogen ions getting 4 electrons, and it will give us 2 moles of 2 molecules of hydrogen gas, 2 molecules of hydrogen gas. So basically, we are going to see the difference happening here at the anode. The difference that we are seeing here is actually at the anode, with a simple reason that the hydroxide ions and chloride ions have they have a small difference in their standard electrode potentials here, which is actually contrary to what we see in hydrogen ions and sodium ions, which actually have a very big difference as far as the standard electrode potentials are concerned. Now let me get to that factor, and this is the nature of electrons. Now, we've been talking about the use of inert electrons. That is, for example, graphite. We can talk about platinum, and so on and so forth. Maybe we use the 2 there. Now, if we are going to use reactive electrons, for instance, we use, for example, copper electrodes here. Something will happen here. Something will happen because these copper electrodes here, they have a high tendency. They have high tendency of actually losing electrons. They have a high tendency of losing electrons here than hydroxide ions. So in this particular case here, if you're going to use copper electrodes here, the reactions at the anode will be affected. I'm specifying anode because at the anode, that's where we lose electrons. And therefore, if you're using a metal that loses electrons more readily or loses electrons, because what we mean by reactive electrodes, that means they lose electrons here, that means you're going to affect the reaction at the anode. Now have a look at this here. I'm using, for example, copper sulfate. I'm going to use copper electrodes. Let's see exactly what happens at the anode here. Now at the anode here, which ions will be attracted here? Of course, I'm going to talk about the sulfate ions. I'm going to talk about the hydroxide ions. By now, we need to understand that all aqueous solutions will have hydroxide ions and hydrogen ions automatically due to the water, which have to dissociate into hydroxide ions and hydrogen ions. Now, with these 2 here, what happens is as much as they will be attracted at the anode, much as they are attracted to the anode, what actually happens here is that instead of them losing electrons here, what will be happening here is that the copper metal here, or the copper anode, will actually dissolve. Look at that. The copper metal will actually dissolve because it can lose electrons better than both of them. And as it loses electrons, of course, it is going to form the copper ions plus the 2 electrons. That's what we're talking about. So in other words, what you're going to observe here is that the copper will actually be dissolving. We are going to see this copper dissolving. It will be dissolving as it releases copper ions into the solution, and of course releasing electrons. Now this one is a very important theory here when it comes even to purification of metals. Even for example, when you purify something like copper metal, during the purification, of course, my pure copper will be put at the anode, where the anode actually will be dissolving. The anode will be dissolving, releasing the copper ions, and then the copper ions can actually get to the cathode, where they are going to gain electrons and will form copper metal. Now let me talk about the cathode. Now with cathode here, of course, copper ions and hydrogen ions will be attracted. Copper ions and hydrogen ions will be attracted. Now we get back to the electrochemical series. you realize that copper ions actually are more positive. They have a higher positive standard electrode potential than hydrogen. That means that copper ions easily gain electrons compared to hydrogen ions. And therefore that goes without saying here that the copper ions are the ones to gain electrons, and of course will form the copper solid. Will actually form the copper solid. That is what we are talking about. Now, that means here that if you're going to use reactive electrodes, the anode will be affected, while the cathode here may not be affected. So what we're going to observe here is that you'll see the cathode. The cathode increases in mass. Because what is happening as the copper ions gets to the copper electrode here, as they get here, what you're going to observe here is that they come here, they'll be gaining electrons and forming copper metal, which actually accumulates on my copper cathode. Then on the other side here, we are going to see a change in mass. The mass will be reducing, and it's important maybe to note here that if I'm talking about maybe pure copper metals here, we are going to have the changes in mass will be the same. Here. Now, if, for example, the anode here reduces by 2 grams, then you're going to realize here the cathode, it increases by 2 grams. That is what we are simply talking about. Now, let's just mention here, I think it will be important here, we do mention about if we are using the graphite electrodes. If we are using the graphite electrodes here, what difference would we actually have? It's important maybe here. Now, if I'm using inert electrodes here, what I would expect here is that at the anode, of course, I have hydroxide ions and I have the sulfate ions. Look at that. Hydroxide ions and sulfate ions. So here now, the fact that we have inert electrodes, the hydroxide ions with higher tendency to lose electrons, we lose electrons, and by now we need to know this equation here, very important. We're going to have 4 hydroxide ions forming 2 waters or 2 molecules of water plus oxygen, and something maybe 4 electrons here. Then at the cathode, this will not be affected. This one will not be affected here. I've talked about the copper ions and hydrogen ions being attracted here because they're positively charged here, and obviously here copper ions with higher tendency to gain electrons will gain the 2 electrons here and form the copper solid. That's what we are simply talking about. Now, some other maybe differences that we may be able to observe about maybe from the cathode, maybe here where we are with the anode here, we are producing oxygen gas. That is when we have graphite electrodes here. There's some graphite electrodes. Graphite electrodes. We are using graphite electrodes here. The difference here will be at the anode, and then maybe we can also maybe mention something about the issue of the concentration. What happens with the concentration here? The concentration of the electrolyte in this particular case will not change. Why? Because the copper ions here that are being discharged at the cathode are being replaced by the ions that are being formed at the anode. So therefore the concentration in this particular case here does not change. With the anode, of course, the copper ions being discharged here are not being replaced. That means that the concentration here of the electrolyte will reduce. At the same time, we are also discharging water in form of hydroxide ions, and therefore the concentration here of the electrolyte here may be affected slightly by that. Then maybe I can also mention about the pH. Now, what is happening here? We are discharging hydroxide ions, while the hydrogen ions remains the same. What does that mean? At the end of the day, the concentration of hydrogen ions will be higher than hydroxide ions. That means again that the pH in this particular case to be lower. So the solution becomes acidic. The solution pH reduces. The solution's pH reduces. That means the solution becomes, or the electrolyte becomes acidic. And basically that is what we are talking about. So please kind of note that the electrodes that you use here can actually affect the product formed at the anode and at the cathode. Yeah.